Tonight, we follow the story of Pluto, the forgotten world at the edge of our solar system. Welcome to the Orbit for Sleep channel. Here, science moves slowly, quietly, and without urgency. Let us follow the orbit of science and drift gently towards sleep. You arrive at the outer edge of the solar system, far beyond the familiar paths of the planets you learned as a child. Here, sunlight is no longer warm or bright. It is thin, delayed, and faint, taking more than 5 hours to reach this distant region. In this quiet darkness, a small world continues its slow journey around the Sunday. It is known today not by a name, but by a number, 134340. This world was once called Pluto. For much of the 20th century, it held a secure place as the 9th planet, memorized in classrooms and printed in textbooks. Its discovery in 1930 expanded the known boundary of the solar system and reshaped how humans imagined their cosmic neighborhood. At that time, simply finding a new planet felt like adding a new room to a familiar house. As telescopes improved, the picture began to change. Astronomers noticed that Pluto was unusually small and followed a tilted, elongated path compared to the other planets. It moved through a region filled with countless icy bodies, now known as the Kuiper Belt. This area is less like a single object and more like a vast field of frozen remnants left over from the early solar system. In everyday terms, the shift can be compared to reorganizing a city map. A distant village may once have been marked as a major destination simply because nothing else nearby was known. As more towns are discovered, that village does not disappear, but its role on the map changes. Pluto underwent a similar transition. In 2006, the International Astronomical Union updated the definition of what it means to be a planet. The new criteria focused on size, shape, and the ability to clear surrounding space. Pluto met some of these conditions, but not all. As a result, it was reclassified as a dwarf planet and assigned the catalog No. 134340. This change was not a loss of importance, but a refinement of understanding. Pluto did not shrink, cool, or drift away. Only human classification shifted. The world itself remained the same silent sphere of ice and rock, orbiting at the edge of the sun's influence. What makes this moment powerful is not the number itself, but what it represents. 134340 reflects how scientific knowledge evolves. As observations deepen, categories adjust, and certainty becomes more precise. The forgotten world was never truly forgotten. It simply revealed that the solar system is more complex, more crowded, and more subtle than earlier generations could see. In that distant darkness, Pluto continues its slow orbit, unchanged by human debate, carrying with it a quiet reminder that understanding grows by letting old labels rest. The distant world, known as 134340, continues its slow journey around the Sun, following an orbit that stretches far beyond the familiar planets. Nothing about its motion signals uncertainty. It travels with steady precision, guided by gravity alone. Yet the way humans describe this world changed, not because of movement in space, but because of movement in understanding. For much of the 20th century, the solar system appeared simple. 8 large planets followed relatively orderly paths, and one small, distant 9th planet circled at the edge. This picture felt complete. The boundaries were clear, and the categories felt stable. That clarity began to dissolve as instruments improved and observations extended farther into the darkness beyond Neptune. Astronomers discovered that the region around 134 1-340 was filled with many icy bodies. These objects shared similar orbits and compositions, remnants left behind from the early formation of the solar system. Some were only slightly smaller than 1-340 itself. The outer solar system revealed itself not as a lonely frontier, but as a crowded disk of frozen worlds. This discovery created a quiet tension in classification. If one object in this region was called a planet, consistency suggested that many others might deserve the same title. Scientific language depends on shared rules. Without them, comparison loses meaning. In response, astronomers sought a definition that described what planets do, not simply where they are. In 2006, an official definition was adopted. A planet, under this framework, must orbit the Sun, be massive enough to form a nearly round shape, and clear its orbital neighborhood of other comparable bodies. The first two conditions described 1-340 well. The third reflected a distinction between dominant worlds and members of a population. 1-340 shares its orbital zone with many objects of similar scale. It moves among them rather than controlling the region through gravitational dominance. This single criterion placed it into a different category, one that acknowledges both its complexity and its environment. A useful everyday comparison appears in how cities define neighborhoods. A standalone house on open land feels distinct. When many similar houses surround it, the same building becomes part of a larger group. The structure does not change, but its context does. Scientific classification works through the same principle. Reclassification did not remove importance. It sharpened perspective. By recognizing 1-340 as part of a broader family of distant objects, astronomers gained a clearer view of how the solar system assembled itself from countless fragments. The change reflects growth in knowledge rather than loss, aligning human language more closely with the architecture of space. Beyond the major planets, beyond the region where gravity sculpts large, dominant worlds, 1-340 continues its steady orbit. Its path does not suggest simplicity. Instead, it reflects a category of objects shaped by cold, distance, and time. To understand what 1-340 really is, attention shifts away from titles and toward physical reality. At its core, 1-340 is a dwarf planet. This term does not describe size alone. It refers to a body that orbits the Sun, has enough mass for gravity to pull it into a nearly spherical shape, yet remains part of a larger population rather than dominating its orbital zone. This definition places it between the familiar planets and the countless smaller fragments scattered through space. The structure of 1-340 reflects its origin. It formed from the same early solar system material that built planets, but in a region where temperatures were low and collisions were gentler. Rock and metal settled toward the center, while layers of frozen water, nitrogen, and methane accumulated above. Over time, gravity organized these materials into a compact, layered world. This composition gives 1-340 characteristics, unlike the inner planets. Its surface behaves less like solid ground and more like slow-moving ice. At extremely low temperatures, materials such as nitrogen ice can flow gradually, reshaping landscapes over long periods. What appears frozen and still is, on geological timescales, quietly active. A useful comparison appears in everyday life when considering glaciers on Earth. From a distance, they seem motionless, yet measurements reveal slow, constant movement driven by gravity and pressure. In a similar way, the surface of 134340 changes subtly, driven by physics rather than heat. The discovery of these properties became clear through direct observation in 2015, when a spacecraft passed close enough to resolve surface features in detail. This encounter transformed 134340 from a distant point of light into a complex world with plains, mountains, and layered ice deposits. The data confirmed that dwarf planets can be geologically rich despite their size. In the broader structure of the solar system, 134340 belongs to the Kuiper Belt, a vast disk of icy objects extending beyond Neptune. It represents the larger, more organized members of this region, offering insight into how small worlds evolve when isolated from strong solar heat. Understanding what 134340 really is requires letting go of hierarchical labels. It is not a failed planet or a diminished one. It is a fully formed world shaped by different conditions, revealing a version of planetary development that unfolds quietly at the edge of the sun's reach. Far from the steady, circular paths traced by the inner planets, 134340 follows a journey that feels unhurried and unconventional. Its movement through the solar system reflects the conditions of the distant region where it formed, a place shaped more by long-term balance than by immediate force. The orbit of 134340 is elongated rather than round. At times, it travels closer to the Sun than Neptune. At other points, it drifts far outward into colder space. One full circuit takes approximately 248 Earth years, a span long enough that a single season on this world lasts longer than an entire human lifetime. This slow rhythm defines nearly every aspect of its environment. Unlike the major planets, 134340 does not move along the same flat plane as most objects in the solar system. Its orbit is tilted, carrying it above and below the primary disk where planets reside. This inclination reflects the gravitational influences present during the early solar system, when massive bodies shifted positions and scattered smaller worlds outward. Despite crossing Neptune's orbital distance, collisions do not occur. The two bodies are locked in a stable gravitational pattern known as orbital resonance. For every 3 orbits Neptune completes, 134340 completes 2. This rhythm keeps their paths synchronized, ensuring long-term stability despite apparent overlap. A familiar comparison can be found in everyday traffic patterns. 2 roads may cross at different levels, allowing vehicles to pass without interference. In a similar way, resonance acts as a timing system, guiding motion so that close encounters are avoided. This orbital behavior preserves the world over billions of years. Rather than being chaotic or accidental, the motion of 134340 represents a stable outcome of gravitational negotiation between larger planets and smaller bodies. It carries the imprint of ancient rearrangements that shaped the outer solar system. The elongated path also drives dramatic environmental change. As 134340 approaches the Sun, surface ices slowly vaporize, forming a thin atmosphere. As it recedes, that atmosphere freezes and settles back onto the ground. Motion and climate remain inseparable, linked by distance and time rather than heat and speed. Through its orbit, 134340 demonstrates that movement in space does not require urgency. Stability can emerge from slow repetition over centuries and millennia. This quiet path continues to trace the boundary between the known planets and the deeper outskirts beyond. As 134340 continues its distant orbit, its presence highlights a quiet but important boundary within the solar system. This boundary is not marked by a line in space or a physical barrier. It exists instead within human understanding, where language meets observation. For much of the 20th century, the word planet carried a simple meaning. A planet was a large body orbiting the sun, distinct from stars and moons. This definition worked well when only a small number of such bodies were known. As observations expanded beyond Neptune, the simplicity of that picture began to fade. The outer solar system revealed a wide population of icy objects, many sharing similar sizes, compositions, and orbital paths. Worlds like 134340 appeared not as isolated exceptions, but as prominent members of a broader family. The need for a clearer boundary became unavoidable. In 2006, astronomers adopted a definition that focused on behavior rather than appearance. A planet must orbit the sun and be shaped into a near sphere by its own gravity. It must also dominate its orbital zone, meaning it has cleared nearby objects of comparable size through gravitational influence. This final condition separates planets from small worlds that coexist with many neighbors. 134340 meets the first two conditions with ease. Its gravity pulls it into a rounded shape, and its motion remains firmly tied to the sunday. The distinction arises from its environment. It travels within a region filled with other icy bodies, sharing space rather than controlling it. An everyday comparison appears in the difference between a single large building standing alone and one located within a dense neighborhood. The structure itself may be substantial, but its role changes when surrounded by similar forms. In science, context often defines category more strongly than size. This boundary does not diminish the complexity of worlds like 134340. Instead, it clarifies the architecture of the solar system. Dominant planets shape their surroundings. Smaller worlds preserve the original patterns of formation, remaining embedded within ancient populations. By recognizing this distinction, astronomers gained a more accurate map of how matter is organized around the sun eye. The line between planets and small worlds reflects differences in gravitational influence, not in significance. Both types of objects contribute essential pieces to the story of planetary evolution. Beneath the quiet surface of 134340 lies a structure shaped by cold, pressure, and time. From a distance, this distant world appears small and inert. Closer examination reveals an interior that is layered, organized, and quietly dynamic, even at the far edge of the solar system. At its center, 134340 is believed to contain a rocky core. This dense interior formed early, when heavier materials sank inward under gravity. Surrounding this core is a thick mantle composed largely of water ice. At the temperatures found here, water behaves less like the ice familiar on Earth and more like solid rock, capable of supporting mountains and deep structural layers. Above this icy mantle lies a surface dominated by frozen nitrogen, methane, and carbon monoxide. These substances freeze at extremely low temperatures and respond quickly to small changes in sunlight. As 134340 moves along its elongated orbit, these surface ices shift between solid and vapor, slowly reshaping the landscape over long periods. This layered structure allows internal heat to persist. Although small compared to major planets, 134340 retains heat left over from its formation, along with energy produced by the slow decay of radioactive elements in its rocky core. This energy moves outward, gradually, influencing the behavior of surface ice. A familiar comparison can be found beneath Earth's polar ice sheets. Deep below the frozen surface, pressure and residual heat allow ice to flow and adjust. The motion is not fast or dramatic, but steady and persistent. In a similar way, the interior of 134340 supports slow geological activity, driven by physics rather than weather. Evidence for this internal complexity became clearer after close-range observations in 2015. Images revealed fractured terrain, uplifted regions, and broad plains that suggest resurfacing rather than permanent stagnation. These features indicate that internal layers interact, even in a world where sunlight is weak. The internal structure of 134340 challenges the idea that small, distant worlds are frozen in time. Instead, it shows that layered interiors and gentle internal energy can sustain change far from the Sunday. In the architecture of the solar system, even the most remote bodies can remain internally alive, shaped quietly from the inside outward. Surrounding 134340 is an atmosphere so thin that it barely separates surface from space. It does not form a stable, continuous shell like Earth's air. Instead, it exists as a temporary state, appearing and disappearing in rhythm with distance and temperature. This atmosphere is composed mainly of nitrogen, with smaller amounts of methane and carbon monoxide. These gases originate directly from the surface. When sunlight reaches the frozen ground, even weak warmth is enough to cause surface ice to slowly sublimate, shifting from solid directly into gas. The result is a faint envelope that clings lightly to the world before thinning into vacuum. As 134340 travels along its elongated orbit, the atmosphere responds predictably. When it moves closer to the sun, surface ices warm slightly and release more gas. Atmospheric pressure increases, though it remains far lower than anything experienced on Earth. As the world drifts farther away, temperatures fall and the atmosphere freezes out, settling back onto the surface as frost. A familiar comparison appears on Earth during very cold, dry mornings. Frost forms directly from water vapor in the air, coating surfaces without ever becoming liquid. On 134340, this process operates on a planetary scale, with the entire atmosphere slowly cycling between ground and sky. Despite its fragility, this atmosphere plays an important role. It transports heat and material across the surface, redistributing frozen nitrogen and shaping terrain over long timescales. Winds are gentle and sparse, yet sufficient to influence how ice accumulates and erodes. Observations made during a close flyby in 2015 revealed layers of haze suspended high above the surface. These hazes form when sunlight interacts with methane, triggering chemical reactions that produce complex organic particles. Over time, these particles drift downward, subtly altering surface color and composition. The atmosphere of 134340 demonstrates how even minimal energy can sustain complexity. It exists at the edge of stability, governed by slow cycles rather than constant motion. In the outer solar system, atmosphere does not require thickness to matter. Even a fragile veil can connect surface, sunlight, and time into a continuous, quiet process. Across the surface of 134340 stretch vast plains that appear smooth, pale, and motionless. At first glance, these regions resemble frozen deserts, untouched and permanent. Over longer timescales, they reveal a different story, one shaped by slow movement rather than sudden change. The most prominent plains are composed primarily of nitrogen ice, mixed with smaller amounts of carbon monoxide and methane. At the extremely low temperatures of the outer solar system, nitrogen becomes solid, yet it remains unusually soft. Under its own weight, this ice can deform and flow, behaving less like brittle rock and more like a very slow liquid. This behavior allows large regions of the surface to renew themselves. Ice gradually migrates from higher ground into lower basins, smoothing impact scars and erasing older features. As a result, some plains on 134340 show remarkably few craters, indicating that the surface has been reshaped relatively recently in geological terms. A familiar comparison exists in thick honey placed in a cold room. It does not pour or splash, yet over time it slowly spreads and levels itself. In a similar way, nitrogen ice on 134340 creeps across the landscape, guided by gravity and subtle temperature differences. Beneath these plains, internal heat plays a quiet, supporting role. Energy rising from the interior warms the base of the ice layers, allowing movement to continue despite the weak sunlight. The process unfolds over thousands to millions of years, invisible in the short term, but powerful in cumulative effect. Evidence of this activity became clear during close observations in 2015. Images revealed cellular patterns across the plains, formed by convection within the ice itself. Warmer material rises slowly, cools near the surface, and sinks again, creating a repeating structure that signals ongoing motion. These flowing plains demonstrate that 134340 is not a frozen relic. Its surface participates in a gentle cycle of renewal, driven by physics rather than weather. In the distant solar system, even ice can behave dynamically, reshaping a world through patience and time rather than force. Time moves differently on 134340, not because clocks behave strangely, but because the planet's motion stretches change across centuries rather than days. Seasons here are not brief transitions. They are long states that reshape the surface, the atmosphere, and the balance between light and cold. 134340 completes a single orbit around the Sun in about 248 Earth years. As it travels along this elongated path, its distance from the Sun varies greatly. When it moves closer, sunlight grows slightly stronger. When it drifts farther away, temperatures fall deeply. Each phase lasts for decades, allowing slow processes to unfold fully. The axial tilt of 134340 adds another layer of complexity. Its axis is tilted by more than 120 degrees, causing one hemisphere to face the Sun continuously for long periods while the other remains in prolonged darkness. These conditions create seasons unlike those on Earth, where day and night alternate regularly. During extended summers, surface ice absorbs weak sunlight and begins to sublimate. Nitrogen and methane transition from solid to gas, thickening the atmosphere and redistributing material across the surface. In extended winters, the reverse occurs. Gases freeze and settle back onto the ground, forming new layers of frost. A familiar comparison appears in regions on Earth that experience polar day and polar night. In places near the poles, sunlight can last for months or disappear entirely. On 134-340, this effect is amplified across decades, allowing seasonal processes to reshape entire landscapes. These slow seasonal cycles help explain why different regions of the surface look strikingly varied. Some areas preserve older terrain, while others appear smoother and younger. Climate, motion, and chemistry remain tightly linked through time rather than weather. Observations made during close study in 2015 confirmed that seasonal change is an active force on 134-340. Atmospheric pressure, surface frost, and haze layers all respond to distance and orientation. The planet does not simply endure the cold. It adapts continuously, guided by predictable cycles. Extreme seasons reveal a broader truth about distant worlds. Change does not require speed. On 134-340, transformation unfolds slowly, shaped by long exposure rather than sudden events. Over centuries, these quiet seasons become the primary architects of the landscape. Orbiting alongside 134-340 is a companion that reshapes how this world is understood. Charon is not a small, distant moon. It is large relative to its primary, forming a system that behaves less like a planet with a satellite and more like a paired arrangement moving through space together. Charon is about half the diameter of 134-340, an unusually large proportion by solar system standards. Because of this balance, the center of mass of the two bodies lies outside the surface of 134-340. Both objects circle this shared point, locked in a slow, mutual orbit. This configuration is known as a binary system. Rather than one body dominating the motion, both contribute significantly to the gravitational balance. Each keeps the other in a stable rhythm, rotating once for every orbit they complete around one another. As a result, the same face of Charon always points toward 134-340, and the same face of 134-340 always faces Charon. A familiar comparison appears in paired ice skaters spinning together while holding hands. Neither skater acts as the sole center. Their motion depends on shared balance, timing, and mutual pull. In a similar way, gravity binds these two distant worlds into a coordinated system. The origin of this pairing likely traces back to a collision early in the solar system's history. In the outer regions, impacts were slower and less violent than those closer to the Sunday. Material ejected during such an encounter could have gathered into Charon, leaving behind two bodies bound by gravity rather than merging into one. This binary relationship influences the internal and surface behavior of both worlds. Tidal interactions in the past may have generated internal heat, contributing to geological activity. Over time, these forces settled into the stable configuration observed today. Observations during close study in 2015 revealed stark differences between the surfaces of Charon and 134-340. Charon appears colder and more uniform, with vast canyons and a reddish polar region formed by captured atmospheric particles. Together, the pair present a contrast that deepens understanding of how similar materials evolve under different conditions. The relationship between 134-340 and Charon shows that worlds in the outer solar system are shaped not only by distance from the Sun, but by companionship. In this quiet region of space, stability can arise from partnership, with two bodies sharing motion, history, and time. The story of 134340 altered more than a single label. It reshaped how planets themselves are understood. As observations expanded into the outer solar system, this distant world became a turning point, prompting a reconsideration of long-held assumptions. For much of the 20th century, planets were defined by familiarity. Large bodies that circled the sun and appeared distinct were grouped together with little need for precision. This approach worked, while only a few examples were known. As technology advanced, that simplicity no longer matched reality. The discovery of many icy worlds beyond Neptune revealed a crowded region with shared characteristics. Objects similar in size and composition to 134340 followed comparable paths. Treating one as a planet while excluding the rest created inconsistency. Science depends on definitions that apply broadly, not selectively. In response, astronomers shifted focus from appearance to behavior. The revised framework emphasized how a body interacts with its surroundings. A planet became a world that not only orbits the sun and forms a rounded shape, but also exerts gravitational dominance over its orbital zone. This criterion reflects influence rather than prominence. 134340 played a central role in clarifying this distinction. By existing within a population of similar objects, it highlighted the need for categories that reflect environment. The change did not reduce knowledge. It refined it, aligning language with observation. An everyday comparison appears in how transportation systems are classified. A road, once considered a highway, may later be reclassified as a local route as networks expand. The road itself remains unchanged. Only its role within a larger system is redefined. This shift in planetary definition improved understanding across the solar system. It separated dominant planets from preserved remnants of early formation. Both categories gained clarity, allowing scientists to trace how matter organized itself over time. Through 134340, the concept of a planet matured. The change reflects the growth of science itself, where expanding knowledge demands more careful language. In this way, a distant world quietly guided a broader understanding of how the solar system is structured. The distant position of 134340 preserves a record from an earlier time. Far from the sun's heat and major planetary reshaping, this world has remained a quiet archive of how the solar system first took form. In the early stages of solar system formation, a vast disk of gas and dust surrounded the young Sunday. Within this disk, material collided and gradually assembled into larger bodies. Close to the sun, intense heat and frequent impacts transformed these objects rapidly. Farther out, in colder regions, change occurred more slowly. 134340 formed within this distant environment. Its composition reflects the conditions of that era, containing ices and materials that would not survive closer to the Sunday. Water, nitrogen, methane, and carbon monoxide froze into stable structures, preserving chemical information from the solar system's earliest phases. The presence of many similar objects in the Kuiper Belt supports this picture. Rather than being an isolated anomaly, 134340 represents a class of worlds that avoided extensive melting and differentiation. These bodies retain features that were common before planets fully settled into their current arrangements. A familiar comparison appears in geological layers on Earth. Deep rock strata preserve conditions from long before the present surface formed. In the same way, Distant icy worlds act as time capsules, holding patterns that inner planets have long since erased. Gravitational interactions during the solar system's youth scattered many objects outward. As giant planets shifted position, smaller bodies were redirected into distant orbits. 134340 carries the imprint of this migration, reflecting a period when planetary paths were still being negotiated. Observations made during close study in 2015 confirmed that this world contains complex geology rather than uniform simplicity. The combination of preserved materials and subtle internal activity offers insight into how early planetary building blocks behaved when left largely undisturbed. Through 134340, scientists gain access to an earlier chapter of solar system history. It demonstrates that understanding the present arrangement of planets requires studying the quiet survivors of formation. In their stillness, these distant worlds retain the memory of beginnings. Distance shapes perception. In the case of 134340, distance reduces a complex world to a faint point of light. For much of its observational history, this distant body existed at the edge of detection, where instruments approached the limits of what they could resolve. Human senses evolved to operate within a narrow range. Sight, hearing, and touch are tuned to nearby scales, quick feedback, and strong signals. Beyond these ranges, experience relies on tools. Telescopes extend vision, sensors translate invisible signals, and data reconstructs what cannot be directly felt. For decades, 134340 was known only through reflected sunlight and subtle shifts in motion. Its brightness changed slightly as it moved, offering clues about size and surface reflectivity. These small variations required careful measurement and long observation periods, revealing how limited unaided perception becomes at extreme distance. A familiar comparison appears when looking at a distant mountain range through haze. From far away, peaks merge into a single outline. Details disappear, not because they are absent, but because distance compresses information. In astronomy, darkness performs a similar function, blending complexity into simplicity. The challenge of observing 134340 highlighted the importance of indirect knowledge. Gravity revealed mass. Orbit revealed interaction. Light revealed composition through subtle spectral signatures. Each method translated physical reality into signals that instruments could interpret. This reliance on measurement reshaped understanding. As technology improved, assumptions gave way to detail. What once appeared as a small, frozen object became a layered world with atmosphere, geology, and seasonal change. The difference lay not in the object itself, but in the reach of observation. Close study in 2015 demonstrated how profoundly distance had shaped earlier interpretations. Features that were invisible from Earth resolved into plains, fractures, and layered ice. Darkness did not hide simplicity. It concealed richness. The limits encountered in observing 134340 reflect a broader truth. Much of the universe exists beyond direct experience. Knowledge grows not by sharpening senses alone, but by extending them thoughtfully. In this way, distant worlds teach as much about human perception as they do about space. The reclassification of 134340 produced a reaction that extended beyond astronomy. It touched memory, attachment, and the way knowledge becomes personal. For many, this distant world had long occupied a familiar place. Learned early, and remembered easily. During the 20th century, the list of planets felt stable and complete. Names were memorized in order, repeated in classrooms, and carried forward as shared cultural knowledge. 134340 stood at the edge of that list, distant yet included. Its position gave it a quiet identity that felt settled. When the definition changed in 2006, the physical world remained the same. What shifted was language. The sense of loss that followed reflected how humans relate to categories. When a label changes, it can feel as though something tangible has been removed, even when nothing material has altered. A familiar comparison appears when a long-known landmark is renamed. The building still stands, the streets remain unchanged, yet the new name feels unfamiliar. Memory resists adjustment, holding on to earlier versions of understanding. The response to 134340 revealed how science intersects with emotion. Scientific classification aims for precision and consistency, but learning often begins with simplified models. When those models are refined, emotional attachment may linger behind. This reaction does not weaken science. It highlights its human dimension. Knowledge grows through revision, and revision can unsettle what once felt certain. Accepting updated frameworks requires letting go of older mental maps. Over time, the emotional response has softened. Many have come to see 134340 not as a planet that was taken away, but as a world that gained clearer context. The shift reflects maturation rather than loss. The feeling associated with losing a planet illustrates a broader pattern. Understanding evolves, and with it, the language used to describe reality. In adjusting to those changes, emotion marks the transition from familiarity to deeper comprehension. Attention often follows size and proximity, yet 134340 continues to hold significance despite its distance. Its importance does not come from dominance or brightness, but from what it represents within the structure of the solar system. One reason this world remains relevant is its role as a representative. 134340 stands among the largest members of the Kappa Belt, offering a detailed example of a population that extends far beyond the major planets. By studying it, scientists gain insight into countless other icy bodies that are too small or too distant to observe closely. Its complexity also challenges assumptions. For many years, small worlds were expected to be simple and inactive. Observations revealed layered geology, flowing ice, seasonal atmospheres, and long-term change. These features demonstrate that planetary processes do not require large size or strong sunlight to operate. A familiar comparison appears in how a single well-studied town can reveal patterns common to an entire region. Streets, buildings, and infrastructure offer clues about broader systems. In the same way, 134340 serves as a reference point for understanding distant solar system environments. This world also connects multiple scientific disciplines. It informs planetary science through its structure, chemistry through its surface and atmosphere, and orbital dynamics through its interactions with neighboring bodies. Few objects link so many aspects of solar system study at once. Beyond science, 134340 holds symbolic value. It marks a moment when expanding knowledge reshaped familiar categories. Its story reflects how science progresses, not by preserving comfort, but by refining understanding. Continued interest also stems from exploration itself. The detailed encounter in 2015 transformed a distant concept into a tangible place. Images and data replaced speculation, reinforcing the idea that even the most remote worlds can be known through careful observation. The lasting significance of 134340 lies in perspective. It reminds observers that importance in the universe is not measured by size or status, but by the clarity it brings to larger patterns. Through this distant world, the outer solar system becomes more intelligible, connected, and complete. Beyond the orbit of Neptune lies a broad region filled with remnants of planetary formation. Within this distant zone, 134340 occupies a prominent position. It is not isolated, but embedded within a population known as the Kuiper Belt, a vast collection of icy worlds that circle the Sun at great distance. The Kuiper Belt extends outward in a flattened disk populated by objects composed largely of frozen water, methane, nitrogen, and rock. These bodies vary widely in size, from small fragments to worlds large enough to form spherical shapes. 134340 ranks among the largest of them, making it a key reference for understanding the entire region. Unlike the major planets, Kuiper Belt objects share space rather than dominate it. Their orbits overlap, tilt, and interact subtly over long periods. 134340 moves within this environment as a structured member, shaped by the same gravitational history that influenced its neighbors. A familiar comparison can be found in an archipelago of islands. One island may be larger and more studied, yet it remains part of a chain formed by the same geological forces. Studying that island offers insight into the entire system without removing it from its context. Observations show that many Kuiper Belt worlds share traits with 134340, including elongated orbits, icy surfaces, and long seasonal cycles. Some exhibit evidence of internal structure and surface change, suggesting that complexity is common rather than exceptional in this region. The presence of 134340 helps anchor understanding of the Kuiper Belt's mass, distribution, and evolution. By measuring its orbit and interactions, scientists refine models of how the outer solar system developed and stabilized after its early period of rearrangement. Close study in 2015 transformed 134340 into a detailed example rather than an abstract member of a distant population. Its well-documented features now serve as a baseline against which other Kuiper Belt objects are compared. Within the Kuiper Belt, 134340 stands as a guidepost. It shows how small worlds organize, persist, and evolve far from the Sunday. Through this single world, the structure of an entire region becomes clearer, revealing the quiet complexity of the solar system's outer edge. As 134340 continues its long orbit, much of its story remains unresolved. The close encounter in 2015 provided a detailed snapshot, but it captured only one moment in a slow and extended cycle. Future missions hold the potential to transform that snapshot into a deeper, continuous understanding. Long-term observation could reveal how surface ice migrates across seasons. Measurements taken decades apart would show where nitrogen and methane accumulate, where they recede, and how landscapes respond to subtle shifts in sunlight. These changes unfold slowly, requiring patience rather than speed. Future instruments may also probe beneath the surface. Radar and gravity measurements could refine models of internal layers, clarifying the thickness of ice shells and the thighs of the rocky core. Such data would help determine how internal heat persists and how it influences surface renewal over geological timescales. A familiar comparison appears in medical imaging. A single photograph captures appearance, while repeated scans reveal function and change. In the same way, repeated visits to 134340 would move understanding from description toward process. Extended study could also deepen knowledge of the atmosphere. Monitoring how haze layers form, evolve, and disappear would clarify chemical reactions driven by weak sunlight. These processes offer clues about how complex molecules form in cold environments, relevant far beyond this single world. The system shared with CERN presents another opportunity. Detailed mapping of their mutual gravity could reveal how tidal interactions shaped both bodies in the past. Subtle variations in motion would act as records of earlier energy exchange. Beyond 134340 itself, future missions could survey neighboring Kuiper Belt objects. Comparing multiple worlds in the same region would test whether the features observed here are common or unique. Each additional encounter would place this world into sharper context. What future missions might discover is not limited to new facts. It includes refined perspective. With time and repeated exploration, 134340 may shift from a remarkable exception to a well-understood example of how distant worlds behave at the edge of the sun's influence. Size often suggests importance, yet 134340 challenges that expectation. Though small compared to major planets, it carries implications that extend far beyond its physical scale. Its characteristics reshape understanding of how worlds form, change, and persist across the solar system. For much of scientific history, complexity was associated with large bodies. Strong gravity, thick atmospheres, and intense heat were thought to be prerequisites for geological activity. Observations of 134340 revealed a different pattern. Even modest gravity and weak sunlight can support layered interiors, active surfaces, and long-term evolution. This realization broadens the concept of what a planetary world can be. It suggests that size alone does not determine potential. Instead, composition, internal energy, and environmental context play equally important roles. Small worlds can preserve processes that larger planets may have erased through violent change. A familiar comparison appears in ecosystems. A small wetland may occupy little area, yet it can support rich biodiversity and influence surrounding environments. Its impact comes from function rather than scale. In a similar way, 134340 influences scientific models despite its limited dimensions. The implications extend beyond a single object. If one distant world can sustain geological motion and atmospheric cycles, many others may do the same. This perspective expands expectations for icy bodies throughout the Kuiper Belt and beyond, including similar regions around other stars. These insights also inform the study of exoplanets. Distant planetary systems contain numerous small, cold worlds that are difficult to observe directly. Understanding 134340 provides a reference for interpreting faint signals from such bodies elsewhere in the galaxy. The importance of 134340 lies not in redefining status, but in refining patterns. It demonstrates that planetary science must account for subtlety and variation, not just extremes. Through this world, the solar system appears less hierarchical and more diverse. Small worlds carry large implications because they reveal processes that operate quietly. By studying them, science learns to recognize significance where it is not immediately obvious, uncovering order within the understated architecture of space. Distance alters emphasis. In the outer solar system, where light weakens and motion slows, importance is shaped less by visibility and more by context. 134340 illustrates how distance can shift what matters, changing prominence without diminishing relevance. Close to the Sun, planetary influence is expressed through mass, gravity, and speed. Large planets dominate their surroundings, shaping orbits and environments decisively. Farther out, interactions become subtler. Objects persist in long-term balance, influenced by gentle forces acting over immense spans of time. 134340 exists within this distant regime. Its separation from the Sun reduces brightness and warmth, but it preserves conditions that are otherwise erased. Distance protects rather than obscures, allowing early materials and slow processes to remain intact. A familiar comparison appears in libraries. Frequently used books sit near entrances, while rare volumes are stored deeper within quiet stacks. The latter are consulted less often, yet they hold information unavailable elsewhere. Their value depends on preservation rather than accessibility. In planetary science, distance plays a similar role. Remote worlds serve as records, maintaining evidence of formation and evolution that inner regions no longer retain. 134340 gains importance precisely because it resides far from disruptive influences. Observations gathered during close study in 2015 demonstrated that distance does not imply simplicity. Beneath faint light, complexity persists in geology, atmosphere, and seasonal change. The challenge lies in reaching these worlds, not in their lack of substance. As exploration expands outward, perspectives adjust. Importance becomes measured by what a world can reveal, not by how prominently it appears in diagrams or memory. Distance reshapes attention, encouraging patience and long-term study. Through 134340, distance emerges as a filter rather than a barrier. It reduces immediacy while enhancing preservation. In the architecture of the solar system, some of the most informative worlds remain those that orbit quietly at the margins. At the edge of the solar system, 134340 is shaped as much by what is missing as by what remains. There is little warmth, no thick atmosphere, and no dominating presence nearby. In this sparse environment, absence becomes a defining condition rather than a limitation. Far from the Sun, energy arrives slowly and unevenly. Without sustained heat, surface processes unfold at a measured pace. Ice replaces liquid, motion replaces weather, and time stretches across centuries. The lack of constant sunlight simplifies interactions while allowing subtle forces to leave lasting marks. 134340 lacks the gravitational authority to clear its surroundings. Instead of control, it exists in coexistence. Nearby objects share space, paths overlap gently, and stability emerges through balance rather than dominance. What is absent in power is replaced by persistence. A familiar comparison appears in quiet landscapes shaped by wind rather than storms. Over long periods, gentle forces sculpt forms with precision. In the same way, the outer solar system favors gradual change, where absence of intensity permits careful preservation. The atmosphere of 134340 appears and disappears, leaving intervals of near vacuum. This absence allows surface materials to settle and record seasonal history without constant disturbance. Layers accumulate slowly, storing information rather than erasing it. Even in exploration, absence plays a role. Long distances limit visits, and extended gaps between observations emphasize patience. Knowledge grows through inference and comparison, guided by what cannot be seen as much as by what can. Through this world, absence becomes informative. Missing heat, missing dominance, and missing immediacy reveal alternative modes of planetary behavior. They show how systems function when stripped of excess influence. 134340 demonstrates that emptiness is not void. In the quiet margins of the solar system, absence defines structure, preserves history, and allows understanding to deepen without urgency. Here, meaning emerges not from accumulation, but from restraint.